Yo, what's up, guys? Welcome back. Episode 128, I think. Yeah, 128 today. We got a Tauros today. Let's take a look at the sound. Can't really do it as deep as that's how it sound today. Um, Looks like we got a little bit. Oh, sorry. I kind of got a text and got distracted, but looks like we got a graph problem. Maybe we'll take a look. We got two sets of edges. There are two undirected trees with n and m nodes with distinct labels and ranges 0 to n minus 1 and 0 to n minus 1 respectively. You're given two 2D integer arrays 1, arrays 2 of lengths n minus 1 respectively, where edges I is equal to a I b I indicates there is an edge between nodes a I and b I in the first tree, and edges 2 blah blah indicates there's an edge between blah blah and second tree. You're given integer k. Node u is target to node v. If the number of edges on the path from u to v is less than or equal to k, note that a node is always a target to itself. Okay, I'm still a little confused. Node u is target to node v. I'm a little confused. Let's take a look at this example. For I, you're going to connect node 1 from the first tree to node 0 from the second tree. I'm a little confused what to do here. You know, I'm not sure. 3372. Let me try and actually understand what the problem was. Maximize the number of target nodes after connecting tree. forest of disjoint trees that are not connected to each other. A number k representing the maximum number of additional edges. What did the comments say? I feel like this is a confusing question. Better explanation. We should just connect a grass with no cycles. First tree has n nodes and is described by edges of one section. Okay. How many nodes in the combined growth both trees plus this one extra edge are reachable from that node within k of fewer steps? I don't know what the best way is to solve this problem. I mean, Connect node 0 from the first tree to node 0 from the second tree. I think I have to watch a video on this one. I'm not sure. I'm still confused with the problem a little bit, but maybe I should look at this code. Man, it's loud.
Hello guys, welcome back to TechDose, and in this video we will see maximize the number of target nodes after connecting trees one problem, which is from Leetcode number 3372. This problem will be based on BFS. So if you don't know about BFS or you are a beginner, then I will recommend you to watch my video on BFS, which is detailed from scratch. The link for it will be present in the description below. This solution will not teach you about what is BFS and how to apply BFS, so I will expect that you know already how to apply BFS. Let's now read the problem statement. There exist two undirected trees with n and m nodes with distinct labels in the ranges 0 to n-1 and 0 to m-1 respectively. You are given two.
We're back in a second. I'm gonna go to the bathroom and then I will be back. 1 second. Okay, I'm back.
Two 2D integer arrays edges 1 and edges 2 of length n-1 and length m-1 respectively, where edges 1 at I denoting ai, bi indicates that there is an edge between the nodes ai and bi in the first tree, and edges 2 at I, ui, vi indicates that there is an edge between the nodes ui and vi in the second tree. You are also given an integer k. Node u is the target to node v if the number of edges on the path from u to v is less than or equals to k. Note that a node is always target to itself. Return an array of n integers answer, where answer at I is the maximum possible number of nodes target to node I of the first tree if you have to connect one node from the first tree to another node in the second tree. Note that the queries are independent from each other. That is, for every query you will remove the added edge before proceeding to the next query. Now this problem statement may be long, but let me explain you overall what it is asking. So it is giving us an edge list which is called edges 1 and another edge list called edges 2. They both are representing two different trees. Let's say T1 and T2. Okay, now if you look at the first example, in this case in the first tree you have 4 number of edges, and in the second tree you have 0 1 2 3 4 5 6, so 7 number of edges, right? Now in this case the tree is undirected type tree. Okay, it is not directed. So if you look at this figure, these edges are undirected and this edge would have been directed. So in this case the edges are undirected. That means if you have an edge from 0 to 1, then it means that you also have an edge from 1 to 0. You can move bidirectionally. So in this particular case, if you represent tree with certain number of edges, then the edge count will always be equals to the number of nodes minus 1 in a tree. There are no redundant edges in a tree. That means there is no cycle and there is exactly one component in a tree. And due to these two properties, we know that in a tree the number of edges will always be equals to number of nodes minus 1. So if I say that the number of edges here is 4, then how do you calculate the number of nodes? The number of nodes will be equals to edge count plus 1. Okay, that will always be true. So if I take edges 1, which is representing tree 1, and find the size and add 1 to it, then I will get the total number of nodes. So edges dot size here will be 4, and if I add 1 it will become 5. That means the first tree has 5 nodes and the second tree will have edges 2 dot size, which will be 7 plus 1, 8 nodes. Okay, so this is how we will be calculating the exact number of nodes in both the trees. Having calculated this, in this problem it is mentioned that both the trees naming, that means the labeling, will start from 0 and it will go till n-1, where n is the number of nodes. So in this case, the number of nodes being 5, it will be numbered from 0 to 4. You see, 0 1 2 3 4. This is how it is numbered in tree 1, and the same goes to tree 2 as well. It will also be numbered from 0 to 8 minus 1, so 0 to 7 in this case as well. If you consider total number of nodes as m in first tree and n in the second tree, then I can say that the node labeling in the first tree will be from 0 to m minus 1, and the node labeling in the second tree will range from 0 to n minus 1. Okay, this is according to the constraint. Okay, fine. Now I hope we have understood everything. Let me go to the constraint, and again I will come back and explain you what the problem is asking. So in this case, the total number of nodes are 10 to the power of 3 in each of the tree. Okay, so n and m value are both maximum 10 to the power of 3. This is the edges length, which is n minus 1 m minus 1, so the number of nodes will be n and m. Then each of the edge list will be u comma v pair, as you saw. This means there is an edge between u and v. Okay, then each of the value will be denoting one of the nodes, so it will always be in the range of 0 to n or 0 to m, right? And the k value was showing actually the number of hops. That means if there is one node x and there is another node y, then there may be multiple number of nodes in the middle. So how many hops is it required to move from x to y? In this case, 1 hop, 2 hop, 3 hops. So this is requiring 3 hops. If the k value was equals to 2, let's say, then y will be not covered from x. Okay, so k value will be defining what nodes we are interested in. Like if you can read this, you are given a value k and node u is a target to node v if the number of edges on the path from u to v is less than or equals to k. That is how you can say that if v can be covered from u. Now let me explain you this example number 1. Okay, so in this case we are given 2 trees and the diagram are already mentioned. So what we are trying to do is, if we have k number of hops available with us, in this particular case the k value is 2. Let's say if we have 2 number of hops available with us, we have to find for each node in tree 1 how many maximum number of nodes I can cover, provided I can do maximum 2 hops. Okay, so what do I mean by this? If you do 2 hops from this 0, how much you can cover? At 0th hop you will be covering this node 0, and the first level you will be covering 1 and 2. At the second level you will be covering 3 and 4. So how many nodes did we cover? 5 nodes exactly we have covered, right? But there is another constraint to it. Another constraint is saying that we can add one edge from a node in tree 1, that means a source node in tree 1, to any node in tree 2. We can add one edge. So if we add that edge, then we have to count what will be the maximum coverage. Let's say that we have added an edge from the source node, where I'm considering 0 to be the source node first time, between 0 to 2. I have added an edge from 0 to 2. So in this case, what will be the coverage with k equals to 2 hops? You will see that 1 hop will be required to reach to tree 2. Okay, 1 hop will be required to reach to tree 2. So in the first hop, we will be covering 1 and 2. The source node will be by default covered at the 0th hop, right? In the first hop we are covering 1, 2 and this 2 as well. So 3 nodes. In the second hop we are covering 3, 4, 7 and this 0. So how many total nodes did we cover? 1, 2, 3, 4, 5, 6, 7, 8. So we have covered 8 nodes in total if we are combining, that means adding an edge between this 0 and 2, so that we will be connecting the source node in tree 1 to any node in tree 2, right? So you have understood how to count. But what it is asking is, it is asking about adding this edge optimally in such a way that it maximizes the coverage. Now if you see another way to add, I could have added this 0 with 0, and in such case I would have covered 9 nodes. Like I would have covered this 1 node, then I would have covered 3 more nodes, so 1 plus 3, 4. Then I would have covered 1, 2, 3, 4, 5 nodes. So another 5 nodes, and that will be equals to 9 nodes, right? So previously how much we had covered? 8 nodes. If we had connected 0 with 2, we had covered 8 nodes. But if I had connected this 0 with 0, then I would have covered 9 nodes, isn't it? So which one is giving me a better result? By adding this 0 to 0, I am getting more coverage with k number of hops, right? So that is why I will try to connect this 0 with this 0. I will be trying this with all the nodes, otherwise how can I be sure if 0 to 0 is the best option? Maybe 0 to 1 would give me the best option, maybe even more coverage, right? So I will have to try with everybody. So if I try to solve this problem for just one source node, let's say for 0, then I will be connecting 0 to 0 and applying BFS starting from the source node and counting the coverage with k number of hops, level order traversal, get the count. Let's say the count is 9. Then I will be disconnecting this and I will be connecting 0 to, let's say, this 1. Okay, and then applying the BFS and maximizing whatever is the count. Then I will be disconnecting this, connecting to 2, and disconnecting to 2, connecting to 3, and so on. I will be continuing to follow this process. So if you follow this process entirely for this given source node, then you will get the maximum value, and that will be equals to 9. When you connect this 0 to 0 with k equals to 2 number of hops, your total coverage will be 9 from the given source node 0, right? So that is why at the 0th index the answer is 9 in the output. Okay, now we have to repeat this process for each of the nodes. So we have done for node 0, we have to repeat it for node 1. Again the same process has to be repeated, isn't it? The total number of nodes here are m, here it is n. So if you apply one time BFS, like for a given source node on 0, if you connect 0 with this 0 and apply a BFS, then it will be m plus n time, right? But if you are applying it for n number of times, then it will be multiplied by n. We have already seen that m comma n both are less than equals to 10 to the power of 3, isn't it? So this will be approximately equals to 10 to the power of 6. Now this is not the only node for which we have to solve. We have to solve for all the nodes. Like the source node will be first time 0, then we will assume 1 to be the source node, then we will assume 2 to be the source node, right? So we have to repeat for all the nodes in tree 1. So another factor, another multiplication factor m comes in. This is also 10 to the power of 3. So the total runtime will be 10 to the power 9 computations, and that will give you a TLE, because I want to solve this problem in less than 10 to the power 8 computations to run within 1 second of time. So this is the brute force solution, and it will not run within 1 second. Okay, so I hope you are clear. Now the idea of optimization is, let's say what we are doing here in this case. In this case we are changing the source node only in tree 1, but we are not doing anything in tree 2. Okay, we just have to connect to tree 2 in such a way that if you apply k minus 1 hops BFS starting from the node in tree 2 by which you are connected, you can maximize the coverage. Why did I say k minus 1 and not k hops? Because 1 hop will be consumed in order to reach from whatever source node from tree 1 to whichever node you are connected to in tree 2. 1 hop will be wasted in going to tree 2. So if you want to apply BFS on tree 2, then you have to apply a BFS with k minus 1 number of levels. Okay, so let's assume that 0 was that optimal node from where if you apply k minus 1 hops, that means 1 hop BFS, then you will be getting maximum coverage. In this case the 0th level will cover one node, which is 0 itself. The first level will cover 2, 3, 1, which will be 3 nodes. So total coverage is 4 nodes. Okay, 4 nodes. So if this 0 is already giving you the maximum coverage with k minus 1 hops, why will I ever bother connecting to any other node in tree 2? Whatever may be the source node in tree 1, if I know that with k minus 1 hops 0 always gives me the maximum coverage, then I will always connect with 0, whatever may be the source node in tree 1. I don't care, I will always connect to 0, right? Now there can be multiple options. In this case 4 will also give me the max answer. That means if I do 1 hop, then at 0th hop you cover 4, and the first hop you cover 3 more nodes, so you will be covering 4 maximum nodes even if you connect to 4. But I don't care about which node you are connected, I just care about the maximum count. So if I know 0 is giving me the maximum count, I will always connect to node 0. Okay, I will always connect to node 0. So if somebody can tell me that You know what? For k equals to 2 value, if you do k minus 1 number of hops starting at node 0, then your total count of coverage will be 4, which is 1 and 3, right? 4 coverage. Then I will not bother to do any more operation in tree 2, and what I will do is, for every source node in tree 1, let's say at 0, I will be trying to apply 2 hop BFS 0 1 2, and I will see what is the number of nodes covered, plus I will add the maximum coverage that I can get from tree 2 if I had connected the source node with the best possible option, isn't it? So that will be 4, so this will be equal to 9, and that is how this answer is 9 here. This is an optimal approach, by the way. I will be showing you in the dry run how to do that. Now for this second number 1, if you have to connect it with the optimal node in tree 2, then it will always be 0. So you know 4 count is always kept for you, and if k value is equals to 2, then the maximum number of nodes that you can cover is 0th level will cover 1 node, plus first level will cover 1 node, plus the second level will cover 1 more node. So this will be 3, and 4 plus 3 will be 7. That is how this is 7. If you see for this node 2, the first level will cover this 2, which is a 0th level. Second level will cover these 3 nodes, and the third level will cover this one. So 5 nodes will be covered, plus 4 nodes covered if you connect this 2 to 0, and that is how you get 9. Okay, and this is how you can calculate for all the nodes. So I think you have got the idea, right? I will explain you the time and space complexity at the end. Now let me show you how to find the best count in tree 2, how to do that pre-processing. So in this case, I have taken the tree 2 and my k value is equals to 2. So in order to find out the best possible coverage from a node, you have to apply BFS from that node, right? And initially I do not know which node will be giving me the best coverage, so I will have to apply BFS from all the nodes. And you know that if you apply BFS from one node, the time complexity is going to be order of v plus e, where v is the number of vertices, in this case it is n, and the number of edges, which is equals to n minus 1, because this is a tree. So the total complexity is going to be order of n if you perform BFS from one node. Yes, I know that k is also mentioned, k number of levels, but you know that k is also less than equals to 1000. So you can try to include that, or you can leave it, because even if k is equals to 1, you could end up covering all the nodes, because all the nodes may be adjacent to just a single node, and still you can have a tree, right? You can still have a tree.
So why use Grammarly over ChatGPT? Well, Grammarly offers expert writing suggestions.
So that is why I'm not considering this k. Now we have to apply BFS from all the node with k minus 1 number of hops, because this is from tree 2, and you know that 1 hop will be required to go from tree 1 to tree 2. So k minus 1 value is 1. This is the 0th level, and this will cover 1 node, and this is the first level, which will cover 3 nodes. So total at 0, we will be covering 4 nodes. Similarly, if you calculate for 1, we are covering 1 node plus 2 more nodes, right? So we will be covering 3 nodes. For 2, we will be covering 1 node and 2 more nodes. That means 3 nodes. So you can keep calculating this, and you will find that 4 will be the maximum. You will also get a 4 value here, where you will be covering 1 node and 3 more node, which will be 4, right? So you can have multiple nodes with the maximum value, but you just care about the count, isn't it? We don't care about the node. So 4 is the best value in this case, where k minus 1 number of hops is allowed. Okay, so we have pre-computed this in order of n square time. Why did I say n square? Because one time BFS requires order of n, and we have to do it from all the n nodes, so that will be order of n square. This is the pre-processing time, right? Now once you have pre-processed, I will not do anything with tree 2. Now I know that I have k equals to 2 number of hops, and I can take each of them one by one as the source node. So if 0 is the source node, apply BFS and count the coverage with k equals to 2 hops. 0th hop, first hop, second hop. So at 0 you are covering 5 number of nodes, plus if you added an edge, if you had added an edge to tree 2, then the maximum coverage you would have got is 4 from the second tree. So add 4 for that, and that becomes 9. So in your answer you will have 9 for node 0. Okay, now you move on to node 1, and you see with k equals to 2 hops, how many nodes are you covering? 1 node and 2 node. This is for level 0, this is for level 1, and this is for level 2. So you are covering 1 2 3 number of nodes, right? So 3 number of nodes and 4 nodes if you had connected this 1 with this 0, the best option, right? So that will give you 7 coverage. So node 1, that means index 1, will have 7 as an answer. Similarly for 2, you can say that I will be covering 5 nodes, 1 3 4 and 1 5. So with 2 hops you cover 5 nodes. So 5 plus 4 will be 9 for this index 2. Then for this 3, 1 2 and then another 2, that means 4. So 4 plus 4 will be 8. So you will be covering 8 for this index 3. And for this index 4, 1 plus 1, that is 2, plus 2, which is 4. So you will be covering 4 plus this 4, which will be 8 for this index 4 as well, right? So we are covering 9 7 9 8 8. If you look at the answer, we are covering 9 7 9 8 8. This is the same example that we had taken, right? So in this case we are applying again
I really believe
m
I would have
times
got
BFS
this
on
if I
the
couldn't-
first tree,
If I just kind of
and you know
understood
each
the
of the
question a little
BFS
better, I
can
think
be
I probably would have
order of
at
v
least got
plus
the
e, and you
brute
know the
force
number of
solution.
vertices are, let's say, m. Edges will be m minus 1 because this is a tree. So the time complexity for each BFS will be m plus m, which is m. And if you apply it m times, then this is going to be order of m square. Okay. Again, for the same reasoning, I am not including k, because even if k value is equals to 1, you may end up covering all the vertices. So I am not taking k into consideration. So if you follow this process, then the pre-processing stage will be n square, and after pre-processing you will take m square time, and you know n is less than equals to 10 to the power 3, m is less than equals to 10 to the power of 3. So the total computations will be around 2 times of 10 to the power of 6, because n square is 10 to the power of 6, right? N square. So simply this will run within 1 second, because this is less than 10 to the power of 8. And the space complexity is going to be n plus m due to the queue that we will be using in the BFS, right? So I hope this approach is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live in filtered and trained case node in the add function, which about the BFS, which takes the start node, which
take away from me. This is the part of me never gonna let you away from me. This is the part of me never gonna take away from me. Visualization say this for tree 1, I believe. Find the best node in tree 2. Now look at me. Okay. Okay. ADJ list, right? Let's do helper function. Helper function to create a adjacency list, right? So we can do, okay. Graph1 is equal to ADJ list edges 1, right? We can do, well, for edge in edges, oh, my back, dude. Um, for edge and edges. So AB is equal to edge if this is the part of me take away from me if graph it's undirected, right? So we have to do it for both. So we do graph A is equal to graph B dot append A, right? And then we would return our graph, right? Got graph 1, graph 2 is equal to AEJ list, edges 2. Okay, let's print graph 2. 0, 1, 2. Okay, so now now we have to pre-process. Okay, we gotta find the best node in tree 2, right? So to find the best node in tree 2, he said in the video that we don't care about the actual node, right? We only care about the best value that we get, right? So we get our best here and we would go, okay, so for I guess for node in graph 2, right? Equal to the length of well, can we go for node in graph 2 technically, right? Because we have zero, 1, 2, 3, 7, 4, 5, 6. I guess that works technically, right? We want to call BFS I guess our current node. I'm not sure, right? Oh, how did I do that? Okay, let's create our BFS function, right? So we do will def BFS. I guess our source, our probably need a visited too, right? Okay. Pass our node, and we can pass in a new set, right? Let's do, okay, so from collections, let's import a DQ, right? Then we go through BFS and we do, okay, well, while we have something in our queue, probably want to append source, right? So we do, well, q is equal to DQ, and q dot append source. I feel like we need something else. We're missing something else, right? I guess for something in graph node, for neighbor in graph node, do node is equal to q dot pop left. Then we go through each neighbor, right? And we append our neighbor. So q dot append neighbor. And we check, well, visited dot add neighbor. If node not in visited, right? We need to check so it doesn't go back. We would do visited, sorry, if let's do the best is equal to 0. Well, let's do make a count is equal to 0, right? And then we do count plus or equal to 1, right? While q node is equal to q dot pop left for neighbor in graph node, if neighbor not in visited, visit dot add neighbor q dot append neighbor count plus or equal to 1. Right. Once we process one level, right, we need to do, well, k minus or equal to 1, right? Let's probably pass in k here, right? We can pass in our k here as well, right? I guess we need k minus 1 because technically when we add the node and come across, we add the node and come across, that's technically 1 already. So it would be k minus 1. Right? K minus or equal to 1. Right? Then we would do, well, if k is equal to 0, we would just want to return our count. Right? Okay, we make our best, or our cur is equal to BFS, right? And then we would do best is equal, we want the max of cur, so the best and cur, right? So then let's print our best. Graph is not defined. Shit, do we have to pass in our graph too? Greater than, not supported between instances of none type and int. So I think we got something wrong here in this BFS. Ooh, 72. Incorrect use of visit. You're passing the same visited set across BFS calls through the use of set at call time, which is fine, but there's no guard for revisiting the source node itself. Okay, minus 1. I guess we could just make the visited set in here. Right, I didn't really think about that, but while q and level is less than k, range length q. We're going level by level. We pop the node and we go, well, for neighbor in graph node, if neighbor not unvisited, q dot append neighbor, we increase our count by 1, then we process 1 level, so we would do level plus or equal to 1, right? Outside of here, once this loop ends, we would return count. It's a little fix up there. That's GD out 4. That's the correct number. Okay, now what we want to do is if we pre-process, so now what we want to do is we want to run BFS on graph 1, right? So this is where we would create an array, right? We go, okay, so for node in graph 1, okay, we would do connections is equal to BFS. We want to pass in our current node. Current node. I think our K and our graph 1, right? Res.append connections plus best. We would return our res. Right? Reason being is that we can reuse its BFS. Well, look at me. This is the part of me. What's wrong here? I'm not sure. I feel like man, this has been a long problem, jeez. BFS, just this. I generally don't know. I'm not sure, man. This seems... visitor.add source. If they've done visit.add name queue. It was just the source. It was just the visited. Nope. I thought I would pass in k minus 1 considering the one edge, but looks like here it might be different. That's so weird, dude. I don't know. You're in two trees. Yeah, I understand that, dude. Like, okay, in each tree. You're not actually merging the two trees at all in your code. You're just summing two separate BFS values. I don't know what I'm doing wrong, dude. I generally don't know. Like, q.append start minus 1. Bro, I don't know how to fix it. I don't know what's wrong, bro. Like 0 1 0 1. K is equal to 0. The output is 2 2, but we get 2 2. He's got a different BFS solution. The way he runs BFS is different. I don't know. Start adjacent K. Q is equal to DQ, Q dot append. I don't know what the -1 is here. Oh, the parent. If V does not equal parent. Okay, that's how he's doing his visited. Okay. Well, Q. Count is equal to 0. While Q and K is greater than or equal to 0. Okay. For something in range length Q, he pops, he goes to the neighbors. For V in graph node, he goes here and does count plus or equal to the length of Q. The only thing I think where well, I don't know what's wrong, dude. 2 0. Output 4 3 5 3 3 3 3 4. Okay, I'm gonna copy this here. I'll do start ADJK. Alright. We got our best. Do our node graph 2 K minus 1 node graph K. I do have the edges here. 1. Okay, let's see if it's the VFS. That's the issue. Nope. Let's see what this says here. Graph 2. Let's call this graph. Graph 1. Well, need to close BFS. That's the way I'm looping? Okay, it was the way I was looping. So I was looping incorrectly. Which is interesting because print I. I was doing the same way, but I wasn't going like in order, I guess. Maybe that was causing an issue. Oh, that could have been causing an issue actually, because I feel like it had to be in order, like this was 0, this was 1, 2, 3, 4. That could be the issue, and mine was all over the place. It was the same thing, but it was just, yeah, anyway. Alright, we'll leave it at that. That was a good problem though. I mean, I learned a lot about that problem. That was a good problem. I really enjoyed that. It took a little while though. Took like over an hour for us to solve that problem. Maybe we can whip out a quicker problem here. Take a look at some graph theory. Maybe we can whip out an easy that we... Nope, there is no easy graph theory problem. Well, that sucks. Shortest bridge, jump game. This is the part of me that you're never gonna take it away from me. Yeah. Let's do number of provinces. Away from me. Where is connected ij is equal to 1 if the ith CD and JC are directly connected, and ij is equal to 0 otherwise. Okay. Try to take a return the number of total provinces. There's 2 here. So if we go 1, 1, 0. did we do this one? May 6th. I'm just confused with this part here. Oh, okay. So this is node 1. Node 1 is connected to node 1 and it's connected to node 2, but it's not connected to node 3. Node 1 is connected node 2 is connected to node 1 and node 2 is connected to node 2, but it's not connected to node 3. Node 3 is not connected to node 1, it's not connected to node 2, but it's connected to node 3. That's what I think this is saying, pretty much. So we can go, okay. Range is connected. We want to pass in. Man, we're running out of time. I gotta go in half an hour. Let me see. How did I do the adjacency list here? I did graphs equal to this, rows equal to length grid, colors equal to populate the graph, iron range rows. Like that. Let's do graph is equal to AJ list is connected. Let's print our graph. I just submitted, bro. Oh my gosh. No, I didn't. Okay. SG out 1, 0, 2. This is an interesting way to do it. Fine, range row. That's the same node. Okay. So now I believe we got to run DFS, right? So FDFS, right? We want to. Oh my gosh, dude. For node in graph node. I guess for node and graph, we want to do call DFS right? We obviously want to pass in that node, right? We want a visited array, right? But we want the visited array here, right? Graph node, we want to pass in visited. We want to pass in our graph. Okay. For node and graph, right? And we check, well, if node not in visited, then we would call the DFS, right? After we get something back, we would count plus or equal to 1, right? Being the number of provinces, right? Then we do our DFS. Where the hell is our DFS here? And we would go, okay, well, man, how do we do DFS? Man, it's been so long when I did it. Holy shit. Okay. Well, first of all, we want to pass in our node. We want to pass in our visited array. And we want to pass in our graph, right? So let's do, well, if trying to think here. Really all we need to do here is add it to our visited array, right? So we would need some sort of base case here, right? For neighbor in graph node, right? We want to do, okay, check, well, if neighbor not in visited, then we want to add our neighbor, right? So we would do, well, neighbor dot, sorry, visited dot add neighbor. We don't really need to return anything, right, in this case, because we're really just checking it here. Is that really all we need, dude? There's no way, like. Now look at me, this is the part of me. If node and visited. Okay. If node and visited, we return. Then we do visited.add node. For neighbor in graph node. Then we call DFS on that node. Yeah, that makes sense, because we're checking if it's visited here, right? We're adding it the node to visited. If it's not, then we're looping through each neighbor, right? We call this, we get our count here. Now pretty much all we got to do here is just return our count. There we go. Oh yeah, we're going to leave it at that. I appreciate you guys watching. Went for about an hour and 20 minutes. Did 2 problems, so got to start getting ready to play some pickleball. So appreciate you guys watching. I will see you tomorrow.